Hello everyone. So in this video we will see importance of common mode rejection ratio and we will relate this concept to the real world. So I have taken one example of ECG measurement. So there will be some electrodes and they will measure your heartbeat and then they will apply this your heart signal differentially to the an ECG machine. So they will sense your heartbeat and they will apply in differential mode so that we can get rid of some common mode noise. So what will be the common mode noise? Common mode noise will be some kind of here. Suppose you have supply and this is 50 hertz. Okay, 50 hertz signal. So this can we can understood as common mode noise. Okay, and this is your heartbeat signal. This is your differential signal. Okay, that you will apply to the ECG machine. So after that they will use some kind of filter here. So after sensing your heartbeat they will use some kind of filter also to remove uh, low frequency noise and high frequency noise, because your heartbeat is nearly here. You can see that they have written 74 bpm, so frequency will be 74 by 16, so it will be like 1.23 hertz. Okay, so this varies person to person or time to time every second. So they will use some kind of filter to filter out some high frequency and low frequency noises. So they have setting. Okay, so here they have taken 0.16 to 20 hertz. Okay, so anything less than this frequency will be filtered out and anything greater than this frequency will be filtered out. Only in this frequency range that will be passed through. Okay, so my heart frequency is 1.23 hertz, so that will pass, and any frequency out of the range will be stopped. Okay, so this is my ECG report. I recently went to the hospital. Okay, so this is frequency, this is common mode noise. Okay, supply frequency, and this is they have written 10 per millivolt. Okay, so this one is 1 so one full bracket will be 5 so two bracket will be 10 Okay, so I am using just rough estimates. It's not uh, a correct approach. Okay, so I just wanted to give a idea how these things work and importance of CMRR. Okay, so suppose this low frequency, this is signal. Okay, so this low frequency have, suppose I'm taking 1 to 2 Okay, and this high spikes is like 10 to 15 Okay, because it's like one and half bracket. Okay, and this one is 1 to 10, 1 to 2 so now they have setting that it's 10 per millivolt. So for a smaller signal, so how much will be 1 1 will be 1 by 10 millivolts. So smaller signal will be, it's like 1 to 10 2 so that will be 0.12 0.2 millivolt. Okay, I'm just trying to know how much a differential signal would be. Okay, so we can, because we don't usually when we simulate we don't know that how much differential small signal will be. So I just wanted to have a real estimate. Okay, and the bigger spike was 10 to 15 mm. So that will be 10 by 10 1 millivolt to 1.5 millivolt. Okay. So here the smaller one is 1 to 2 mm. So that will be zero point 0.1 to zero point 0.2 millivolt, and this one bigger one is uh, 10 to 15 mm. So that will be uh, 1 to 1.5 millivolt. Okay. So now we can uh, take as a differential input signal, like I'm taking the maximum range 1 millivolt to 1.5 millivolt. Okay, for our purpose, we can, for understanding purpose, suppose I'm taking like 15 millivolt. Okay, maximum range at 20 millivolt. So this kind of range we can think of a differential signal applied to any op amp. Okay. Now suppose I'm just taking an example. I'm taking 5T OTA. Okay. So I am taking some example. Suppose common mode signal is, suppose it's a VCM is 200 millivolt, and supply frequency 50 hertz noise, and my this differential signal will be 1 millivolt to 1.5 millivolt. Suppose I'm taking 1 millivolt at frequency of 20 hertz. Suppose I'm taking 20 hertz. It's not 20 hertz, much more or less than we just say here 1.23 hertz. So I'm just taking a higher frequency. So how it will look like? So it will look like this 50 hertz is 20 millisecond time period. Okay. So this will be 200 millivolt, 50 hertz signal. Okay. And top of that, here will be that differential signal, this 1 millivolt, 20 hertz. So you may see and confuse that this is your noise and this is your signal, but not that's not true. This is your noise and this is small, this is our main signal. Okay. So now what will be the signal to noise ratio at the input side? At input side, signal to noise ratio will be 200 1 millivolt of signal and 200 millivolt of noise. Okay, so that will be 1 by 200. 1 by 200th of noise. Now we will calculate signal to noise ratio at the output side. Okay, so before that we will calculate CMRR. Okay, so we know that in a 5T OTA differential gain will be GM of input transistor into RO2 parallel RO4. And what is common mode gain? It's 1 by 1 plus 2 GM of input transistor into resistance of tail current source into GM of input transistor divided by GM of current mirror load. Suppose for approximate calculation I am taking this equal, so that will be cancel out. I am ignoring this one. Okay, so this will come as 1 by 2 GM of input transistor into, and RSS will be, suppose I am taking a MOS current source. Okay, so that will be R0. So this is the common mode gain and this is the differential mode gain. So the signal we had this. So common mode signal was 200 millivolt, 50 hertz, and this signal was, differential signal was 1 millivolt, 20 hertz. Okay, so this will be multiplied by ACM and this will be multiplied by AVD. Okay, and that will come appear as at the output. So what will be the signal at output? Signal to noise ratio at the output. So that will be signal 200 millivolt at the input into the ACM, and okay, so that is 1 millivolt. Signal is 1 millivolt, and that will be multiplied by differential gain. And our noise is 200 millivolt, and that will be multiplied by our common mode gain. Okay, so our signal is getting magnified by differential gain, and our noise is getting amplified by a common mode gain. So this is 1 by 200, and this, what is this? This is AD by ACM. This is nothing but CMRR. Okay, now we will put this value. So this will be 1 by 200 into, what is the AD? It's a GM. Suppose RO2 parallel RO4 is RO by 2 divided by 1 by 2 GM R0. Okay, so it will be GM R0 by 2 into 2 GM R0 into 1 by 200. So this 2 and this 2 will be cancelled out. So this will be 1 by 200 into GM R0 square. Okay, so in a 5T OTA, the CMRR is the order of GM R0 square. Now here I have taken one example of 45 nanometer GPDK. Okay, so this is 45 nanometer GPDK. So I have plotted GM by GDS versus GM by ID. So here GM by GDS is nothing but GM R0. Okay, so this is intrinsic gain of transistor. So maximum I can see here that it's 70.83 to 1, and this is 68.2239. So I am taking just rough approximate as 60. Okay, so I am taking a value of 60. So this will be 1 by 200 into 60 square. So this will be, let me calculate, 60 square divided by 200. So it's 18. And okay, so signal to noise ratio at the output is 18, and signal to noise ratio at the input is 1 by 200. So that is okay, 0.005. Now you can see the difference. High signal to noise ratio means noise is less, signal is high, and low signal to noise ratio means signal is low and noise is high. So just because of that CMRR, okay, that just because of this common mode rejection ratio of order GM R0 square, how much noise we are getting rejected. Okay, if I am taking ratio, that is signal to noise ratio of output divided by signal to noise ratio at the input, so that will be 18 divided by 0.005. So that is a lot. That's okay. So that too much we are rejecting our common mode noise. So this is importance of our high CMRR. So we prefer generally high CMRR in the circuit. Okay, so I hope you enjoy this uh, video. So again, I'm summarizing. So I measure my heart signal. Okay, I give that signal differentially to that ECG machine, and there are some power supply nearby, so that have a 50 hertz frequency. Suppose your bed is ground, but still there will be some noises. Okay, and this is my ECG report. So 74 bpm, its frequency is 1.23 hertz. Okay, so I rough estimated that my heart signal may be between 1 to 2 mm smaller signal and 10 to 15 mm, a bigger signal. So I estimated that can be zero point 0.1 to zero point 0.2 millivolt, smaller one, and the bigger one is 1 millivolt to 1.5 millivolt. Now I tried to figure out how it will look like waveform at the input side. So don't confuse like that smaller one is noise. No, that is signal, and that low frequency 50 hertz, high frequency 50 hertz is our noise. So I calculated a signal to noise ratio at the input. So signal is 1 millivolt and noise is 200 millivolts. So that is 1 by 200. So I have taken one GPTK 45 nanometer. So that I have taken intrinsic gain of an 60. After that I calculated AVD and ABCM. So my differential signal will be amplified by differential gain, and my common mode signal will be amplified by the common mode gain. Okay, so I rough estimated how much that will be signal to noise ratio at the output. So here we can see that there is a lot much we are getting good signal. Okay, we are rejecting very high C noise. So okay, so please let me know if you feel getting any doubt. Okay, bye. Thank you.